This is SQL Friday number, I think, 111, but I'm not sure, to be honest. Our guest today is Dejan Sarka, who first time I saw Dejan present was, I think, on a conference in Denmark. And Dejan did a presentation about fuzzy search using n-grams, and there was a question from the audience, and they have responded with, well, you need to have a basic understanding of mathematics to basically grasp this. But so I think we're going to be in for Dejan is a mathematician, and we will see, I guess we can call it applied mathematics, but it's going to be about using R and Python and T-SQL for data manipulation and data exploration. Did I explain that correctly, Dejan?
Yes, you explained it correctly. Thank you very much.
So, whenever you're ready, Dejan, you're so welcome to SQL Friday.
Thank you very much. So let me share my screen and go to my virtual image. And we are here. So data, sorry, let me move this to another screen. So data overview and manipulation in T-SQL, R, and Python. As Magnus mentioned, and Sarka, I'm getting pretty old, approaching retirement. I've been a trainer and the data platform MVP for more than 20 years, authored, co-authored 19 books so far, and so on. And yes, I actually started with applied mathematics, started in university and so on, and then went to business. So in this presentation, I will talk about basics, about data preparation and data overview for a data science project. In a real project, you typically spend in this area 70–80% of time. The actual modeling, model evaluations, and then deployment takes only 1/4 of the full time of the project. Of course, you need to have good understanding what you have in your data. So I will talk about data sets and explain what are cases and variables, and how do we get the idea about the distribution of values of these variables with statistics, introductory statistics, descriptive statistics, and also mention some graphs. Then we'll talk a little bit about handling missing values and outliers, and how do we create all kind of derived variables, general, and then specific topics like creating numerical variables from strings, discretizing continuous variables, so creating discrete variables out of continuous one. And at the end, I will introduce entropy, a very useful measure for many things, also giving you some information about distribution of variables and some comparisons. Now a little bit about terminology. Terminology comes mostly from statistics, so we analyze cases and we use variables or features for analysis. Now, initially, statistics was developed on data structures like matrices, 2x2, similar to a table, but matrix in general has just values of a single data type. Table, every single column can have all data type. Matrix also have positional access, like you can say, give me a value from row 3, column 2. Table, we need key and column name to get the value. Now, what we analyze, we call a data set. Data set can be represented in some product as a matrix, as a table, or worth mentioning, in R and Python, we use data frames. So a data frame is an object that is kind of mixture of matrix and table. So it has columns with names. Every single column can have different name or must have different name, but it still preserves the order and it still has positional access. In R, you would still find, probably not in Python, but in R, you can still find many functions that still operate on matrices only, but the vast majority of functions in R and Python operate on data frames. And in SQL Server, of course, we have relations represented as tables. Now, before we start analyzing the data, of course, we need to understand what is in our data. So how do we measure data values? And depends on this kind of variables is what we can do with them. Some algorithms expect discrete values only, some algorithms continuous values, and so on. Now, discrete values means we have a limited pool of possible values, like 5, 7, and then we have categorical or also nominal variables. They have no natural order. So there is no order in them. Maybe like we have products and we have different colors. And if you deal with products, there is no natural order in colors like blue, red, green, yellow. But then we have ranks or ordinals. They do have an order, but they do not permit arithmetic. For example, opinion ranks, you evaluate a session with evaluations between, let's say, 1 and 7. 7 is better than 3, 4 is better than 2, and so on. But you cannot say if one person evaluates it with 7 and the other with 2, that both of them evaluate it with 9. Now, continuous values, we have true numerics that support all arithmetic, and we have intervals which are limited on one or on both sides. In business, we very frequently work in with intervals limited on at least one side. For example, temperature starts with absolute 0. Income, let's say, shouldn't be below 0. Many times intervals do not allow all arithmetics. They always allow subtraction. Like if today is 17 degrees centigrade, yesterday it was 13, we can say it is 4 degrees warmer, but 17 plus 13 doesn't make 30 and really a warm day. I see a question. You can use averages, though, in that case, in which case I'm a little bit lost here. In which case you can use averages.
Can I use voice? Is that fine?
Yes, yes.
You mentioned if people score something, like someone scores 2 and someone else scores 7, they don't score 9 together, but they do score about 5 something average, which is a thing you can say. But I think arithmetic is just addition, subtraction, etc. That might just be my lack of terms in English.
Actually, no problem. I mean, average is also consists of sum and division, so not a problem here. As I said, yes, depends on a variable. Some arithmetic, some mathematics make sense, but not everything. The more we go towards true numerics, the more we support all arithmetic. But also, it is really worth mentioning that this division on these variables, these groups, is division based on how we use them, not really natural one. Remember, I talked about colors. Yes, colors do not have natural order. If we talk about products, let's say we have blue bikes, green bikes, and so on, or blue cars, green cars, red cars. But we know that colors have different frequency, you know. So if we use frequency, we can get a continuous variable for colors. Depends how we use them. Also, think about variables like number of children. Is this a discrete or continuous one? It goes typically, let's say, from 0 to 3, 4, 5, maybe 10. So it's not really continuous one, yet theoretically it can go forever. So it really depends. Sometimes you can just decide to use it as continuous one and sometimes as discrete one. So don't forget that this is kind of depending on the business problem you are solving. Then you actually define how these variables, what kind of variables do you have. And that's why we will also talk how you can discretize continuous variables or make numerical variables out of discrete ones if you want to use them in different algorithms that have some specific needs. Now, let's start with basic descriptive statistics, really basic. So why is it called descriptive statistics? Because it describes the distribution of a variable. Of course, we can see the distribution of a variable also with a graph. And which method is better? Actually, both methods are needed. Graph can be very nice for a quick overview, but it's very hard to see, let's say, which variable has better spread, more variability, if you have, let's say, 500 input variables. When you use numerical measures, you can order them by, let's say, standard deviation, descending, and quickly see which one has the more variability, which one less. So both methods are very useful. And in many cases, you have to deal with many variables and simply graphs are not good enough. But why do you need also to check graphs? Because these now numerical numbers that you get from descriptive statistics can be misleading. Let me go to R. I will use RStudio, and this is a famous Ainscope dataset. Ainscope is British statistician, and he already created this dataset in 70, 75, 76. So we have 8 variables, 4 pairs, x1, y1, x2, y2, and so on, with 11 data points. Okay. Now let's do some graphs. Let's check first correlation coefficients. X1, Y1, X2, Y2, X3, Y3, X4, Y4. All correlation coefficients are the same on, let's say, first 3 degrees at least, 0.816. So we could say all of these pairs of variables are equally correlated. Now let's create a simple graph. I will create 4 small graphs, scatter plots of these 4 pairs of variables. Now let's see these scatter plots. And what we can see is that with first pair, we have pretty good distribution. And this could be pretty, this correlation coefficient could be trusted pretty well. With the second pair, what we see is that we have non-linear distribution. So linear function is an approximation. We have polynomial dependency between x and y. So linear regression wouldn't be very useful here. Some kind of polynomial regression would be better. In third pair, we see practically ideal correlation, but the coefficient is too high because of one single outlier. And in fourth case, what we see is there is no correlation at all, but we have one very huge outlier that changes everything, and suddenly you get the same correlation. So you see, this is why it is extremely important to check both numbers and graphs. And let me quickly search for something very nice example, more modern example from 2012, like 40 years younger example. So here we have even dynamic picture. Datasaurus doesn't. So we have dozen pairs of x and y, which all have the same mean on second decimal, same mean, same standard deviation, same correlation coefficient, yet you see the distributions, 12 different distributions. One is even resembling a Tyrannosaurus, so that's why it is called Datasaurus. Datasaurus doesn't. This is what tells you that you should be careful and check both the numbers and the graphs, and then you can get the idea. Now, of course, how do we describe a distribution of continuous variables? We use what is called population moments. First, we check centers of distribution. Arithmetic mean is the most common measure for the center of the distribution, but also probably the first mostly abused statistical measure. We have already seen what can outliers do to this number in this Ainscope quartet. The last pair, just a single value far out of the borders changed everything. So it is very prone on showing suspicious values if we have outliers. Median, we sort these cases by the value of the variable, and we simply read the value at half of the cases. So this one is not very dependent on outliers because we are just reading the median value. Now, to give you another example, just imagine that Bill Gates would join this conversation. In average, we are immediately billionaires. Now, median would be much lower. If median is lower than mean, then it means we have skewed distribution. Lower than mean means we have long tail on the right side. So in this case, with Bill Gates, median would be much lower than mean. If this would be the opposite, then we would have long tail on the left side. Now spread, of course, we calculate variance, and then square root of variance is standard deviation, which again, so how is it calculated? So we started, I think I have later in some slides also some formulas, but just basically from every value, we subtract mean and we square this. And then, so it means every value comes in the equation on second degree. And then there are some other parts of the equation, but this is the important part. What does it mean? Because we have every value on second degree, outliers have even more impact than on average. So we have, again, if spread is very high, we should check if standard deviation is very high. We should also check interquartile range. If interquartile range is much lower than standard deviation, it means tails are really important. So outliers are really big. Skewness tells me on which side, and kurtosis, the fourth population moment, tells me how important these tails are. Anyway, but I already get the idea. If interquartile range is lower than standard deviation, then tails are important. If it's bigger, tails are not important. Now, I want to mention, now skewness and kurtosis are then relative measures for these tails. So skewness tells you relatively how long the tail is on left or right side. Negative means on left side. Absolute number means longer tail, higher absolute number. So you can easily compare skewness between two or more variables. Also kurtosis. Positive kurtosis means tails are important, negative tails are not important. Since this is a relative measure, again, it means you can compare multiple variables to see which ones are those with more outliers. You should be more careful with them. I would also like to make a brief comment on kurtosis. For many years, kurtosis was called pickedness. Now, before that, I forgot to mention something. So, well, formula for skewness starts with every value minus mean on third degree, and kurtosis, every single value minus mean on fourth degree. That's why these moments are also called first, second, third, and fourth population moments. Now, kurtosis was for years called also pickedness. So high kurtosis means that you have a peak near the mean of the distribution. The logic here was high kurtosis means we have long tails. So in tails, we don't have too many cases. So the majority of cases must be grouped around the mean. So we have a peak there. Well, you see, this was completely wrong interpretation. For decades it was used. In 80s, 90s, even I used it in quite a few articles. Everybody used this expression. Until at some moment I read a review of an article and some person wrote, but don't you understand that kurtosis doesn't tell you anything about the distribution around the mean? And of course, immediately when I saw this review, I understood, and I was thinking, how was I so stupid for, I don't know, probably 20 years before I realized this, because I didn't check I didn't doubt in this expression. Now think of it. If we have two values, one, let's say that we have standard normal distribution. One standard normal has mean at 0, standard deviation at 1. And now let's say we have a value that is 1 standard deviation away from mean. So calculation, value minus mean on 4 degrees 1 minus 0 is 1 on 4 degrees 1. Now let's take a value that is 5 standard deviations away from the mean. 5 minus 0 is 5. On 4 degrees, 625. So this value participates in the kurtosis calculation 625 times more than the value that is close to the mean. So the value that is close to the mean is not important at all. And nowadays we call kurtosis also tailedness, not peakedness anymore. Worth mentioning why we called it peakedness. First person that called it peakedness was Pearson, big statistician, the father of modern statistics. And of course, for decades, nobody doubted, nobody checked what Pearson said. We naturally didn't question the big statistical authority, the big authority in statistics. This is a lesson that you have to doubt in everything. So science is about doubt. If you don't doubt, then this is religion. And we are talking about science here. And of course, you cannot check everything, but having a little sense of doubt is always useful. So this is an example how these distributions would look like. And remember, we should always check the graphs as well. What if we have discrete variables? Then we calculate frequency tables and graphs. And what we put there is absolute frequency, simply count, absolute percentage. But then if variable is ordinal, it might make also sense to calculate cumulative frequency and cumulative percentage. For non-ordinal, for nominal variables, this is less meaningful. And of course, we can also show a histogram. And yes, we have median, we have arithmetic mean, we can compare median and mean to get skewness. Mode is the most frequent or common value. This is something that you can also calculate to see if you have a single mode or multiple modes, if you have more than one peak, and then we have, say, we have bimodal, trimodal, or multimodal distribution, gives you some idea. And range, absolute value, maximal minus minimal value, not very useful because of outliers. Interquartile, find the value on 75%. And subtract the value on 25% of data. And this is something that is quite useful. So you can use it similarly like median to check the mean. You can use IQR to check the standard deviation. Let me briefly introduce one concept, degrees of freedom. It's not so important anymore since we usually work with big data sets. But if you would analyze smaller data sets, it might be still important. So what is degrees in freedom? It is a number of distinct value of a variable minus one. What does it mean? Why? If you see this number. It is still very frequently that you show this number also with calculations. What is the number of degrees of freedom? Well, think about, let's start with a simple discrete variable that has two states only. Let's say we have products we are selling, blue and yellow products. If we know that we have 60% of blue products, we can calculate that we have 40% of yellow products. So only one number is free. If we would have, let's say, the third color, let's say red. Now, if we know that blue is 60, red is 20%, we can calculate yellow is 20. So we have three distinct values, two are free, and so on. And the formula for variance, you see, is sum of all values minus mean squared and multiplied by 1 divided by number of degrees of freedom. Of course, if n of values is very big, so if we have n that is bigger than 200, for example, then this is practically 1, practically the same if you use n 1 divided by n or 1 divided by n minus 1. If we have 1 divided by n minus 1, we say this is variance. If it's 1 divided by n, this is variance for population denoted with var p, and then square root of this is standard deviation or standard deviation for population. You know, from T-SQL we have both var and var p, stdev and stdev p. Anyway, as I said, the difference with big data sets, it's so small that in data science, we typically don't care too much about these degrees of freedom anymore. These numbers are absolute, but we can, similarly, like for skewness and kurtosis, we can calculate relative standard deviation or coefficient of variation, simply divide standard deviation by mean. And now we can see which variable is more useful. So more useful for analysis. Variable is useful if it has variability. Constant are useless. Let's say if you have only blue products, you can forecast with 100% accuracy what will be the color of the next product you will sell, of course. So the more variability you have, the more interesting this variable. This is why they are called variables, because they should have some variability. The more variability means the more interesting is for finding some information. And remember also, don't forget, what you are looking for is something you don't know. You are searching for surprise. If you already knew it, then of course the analysis is not really extremely useful. So you are looking for surprise. Now we can compare relative variability of numerical variables. What about discrete ones? So far we have only frequencies distribution. And you will see later that this is where I will need to introduce also entropy. So we will be able to compare relative variability with help of entropy. Now let me go to some examples. And I have examples in different languages. So this is Python. I will just import libraries I need, and I will read data from my Adventure OLZW database with target mail view. I have many interesting variables there. So I need NumPy brings me in Python matrix calculations. Pandas brings the data frame object, Occupy ODBC to connect to SQL Server, and two graphical libraries which will help me drawing the graphs. So let's see the shape of my my data frame is empty, right? Because I didn't actually read the data. I just showed the code. Now it will work better. So I have 18,000 something rows, 13 variables. These are first 10 rows, abbreviated couple of variables. Now, let's start with nominal variable, which is actually ordinal. So we have value counts for education. What is the problem here? Well, you see, I remember I told you there is no strict limit between these categories of variables. Education is here a string, but it has some natural order. It is like what is the number of years needed to get some degree. So it is actually ordinal variable. So let's define it as categorical. So I will show this that education is now, let's go, value counts type is general object. And let's define it as category. Now I find it categorical, but the order here is alphabetical. So let me also define proper order, right? And now I have education with proper order, and now counts are sorted properly. Now, how is this important? Depends on the things you are analyzing. For some analysis, this could be extremely important. For example, if you would like to show income in classes of education, this is a continuous variable in classes of discrete variable is typically represented with box plots or violin plots. And if the discrete variable is not sorted properly, you don't see from the graph that these two variables are actually associated. It would say that education has no influence on income. So let me create a quick plot based on these sorted values. One remark. Remember central limit theorem. So every distribution with enough cases somehow limit towards Gaussian or bell curve. Now, even with discrete variables, if you have enough classes, okay, 5 is hardly enough, but still you can already see that this is somehow resembling bell curve. With 7 and more, this would resemble even more the bell curve. What does it tell you? It tells you that you can trust the numbers you get from descriptive statistics. This is what tells you this graph. If it's not resembling Gaussian distribution, then you should check why not. Maybe you have some specific subset of data. I mean, let's say age of people. If you are analyzing students, then of course the majority of people will be young. But then if you split these young people into small groups, again, you might get kind of Gaussian distribution. So it tells you something that distribution looks quite okay, let's say. Right. We have another possibility like count plot in SMS, and I can show in this clustered column chart two variables. So we have bike buyer 0 and 1 is orange, and we have properly ordered education. And now we can maybe notice that people with higher education tend to buy more bikes than people with lower education. If education was not sorted properly, we wouldn't be able to notice this association. Now, Pandas has data frame has very nice method described that gives you very quick descriptive statistics about single variable. So H, we have number of cases, mean, standard deviation, minimum, maximum, value on first quartile, value on median value, value on third quartile, and maximum. We see that median 34 is slightly lower than mean, so there must be some slight tail on the right side. Of course, we have separate functions we can calculate. We can calculate inter range, maximal minus minimal value. We can calculate interquartile range, which is 17, and we can calculate variance, standard deviation, and coefficient of variability. And what we can see, standard deviation 11.5, while interquartile range was 17. Interquartile range is bigger than standard deviation, so it means tails are not important. I have some tail on the right side, but not really important. I do not need to do anything about outliers with this variable. Let's show graphically age and income. And we have scatter plot of age and income. I only used a couple of cases to make this quickly, this fast. But what we can see is that it's not really linear. It's more like polynomial relationship. Now think about real life. When you are young, you earn less than in Middle Ages, but then when you get older, you start learning less again. I'm already on this declining path. You know, now seriously, I'm an independent consultant, and since I'm approaching retirement, I tend to work less. And since I'm, alone, it means less work, less income. Very simple formula. This is like hours of work and income is connected linearly, but age not. Okay. Now, very useful is joint plot. This one will take a little bit more because I'm using now all, but still was quite fast, all values. And we can see all values. Okay, because there are too many values, scatter plot is not so useful, but we see a marginal distribution. Let's check marginal distribution also as with kernel density graph. This one will take a little even more because this one is really trying to draw every single point. So it will take a little bit more, but you can see also this kind of heat map. And what we can see here is age. Yes, we have long tail on the right, but what we can also see here with income, that the distribution is actually bimodal with some gap in between. And this you can also see from this heat map. So we have already a good idea about distribution. Now we can create also trellis charts. Remember, I created trellis chart is chart with small multiples. I already created one with R. We can also create this in Python, so we can show even more variables in a single graph. So we have yearly income in classes, right, of bike buyer and house owner flock, and we see the distribution of yearly income in these classes. So we can already notice kind of let's say connections, associations between more than two variables. Of course, we have similar things in R. Basically, R is the statistical language. Python is more or less following R, although nowadays Python is also developing very, very quickly. But for example, data frame object is native to R and was simply copied to Python. So we can check like with table function basic distribution. With R, I will also define education as categorical. It's called factor in R, and with proper categories. And let's make plot. And again, since I showed this in proper categories, I see that I have kind of a Gaussian curve, so I can trust this distribution. We have a lot of packages for In R, we have 15,000 additional packages, many of them dealing with basic statistics. So for example, Desker library, we have freq function, we get frequency, percentage, cumulative percentage, and graph. And remember, cumulative percentage makes sense because I properly defined it as ordinal. Summary function is one that gives you basic information about this population moments, minimal value, maximal on first quartile, median, mean. Again, we see that mean is a little bit higher than median, so we have a slight tail on the right side. No, this one is, yeah, mean is bigger than median. So we can have also separate function, minimum, maximum range. We have function for interquartile range out of the box. We don't need to calculate it. And we have variance and standard deviation. And of course, we have fantastic graphic possibilities. I will not go to details how to write its code. Of course, this is not a big deal today, but let me create some kind of presentation 2x2 graph and show couple of these distributions. So I'm showing education and marital status together, histogram of number of cars owned, and total children compared to number of cars owned, but only with a small data set. So I have line chart with few points only. And let's say number of cars owned and bike buyer. And let's say what we can see here, basic distribution of number of cars owned, maximum at 2, right? We see that with education, we have slightly more merit people, blue collar, slightly less single people. We have only 10 cases in the third graph, but we can see that there is some kind of correlation between total children and number of cars owned. And bike buyer, again, we can see that especially people here, non-buyers are 0, especially people with 2 cars tend not to buy bikes. Buyers are mostly people with 0 and 1 car. Okay. Now, what about T-SQL? Can we do things here as well? Yes, we can. We don't have so many different functions, but still many things are possible. So this is like distinct value of commute distance. If we want to sort it correctly, again, this is an ordinal. We have to use case expression. We can calculate count and absolute percentage, and then we can use window functions to calculate also cumulative frequency and cumulative percentage. And yes, we can also, based on absolute frequency, we can even draw a histogram and see the distribution of this variable. For centers, top one with ties is very useful for checking mode. And whether, but of course, it would make sense to group these numbers. If there are too many distinct values, then you will probably always get a single highest value. Median, we can use percentile count or percentile dist functions, this window analytical function. Arithmetic mean, again, we see mean is slightly bigger than median. Range, and interquartile range, and standard deviation, coefficient of variations, these functions come out of the box.
Can I ask you something, Dejan?
Yes, please.
Did you check how in SQL Server 2022 we got some of these statistical functions with approximate functions too? Yes. Did you check how good they are?
Yes. Actually, we have in SQL 19, we have already approximate count distinct, and in 22 approximate percentile continuous and percentile discrete. Now, you see what I am doing frequently is if I do some kind of SQL Server optimization, frequent error when people create indexes with composite keys is they don't put on the first place column with the highest cardinality. So I want to calculate count distinct over all indices. Right?
Yeah.
Now you can imagine how long can this take for multi-terabyte database with big tables. Fortunately, not all tables are that big. So I do it with a cursor and so on copy of data overnight, whatever. But with approximate count distinct, it's like in minutes, and I don't really need an correct number. So Microsoft say these numbers will be in confidence interval plus minus 2%, which is more than good enough. So yes, I find these functions. Actually, this is implementation. I already use approximate count distinct. I didn't use approximate count, approximate percentile, discrete and continuous yet, but probably they will be extremely useful as well, because we are doing an overview here. We don't need exact numbers. And they are extremely important. I hope we get more functions like this. Now, let me give you the idea about performance. So we know that Transact SQL is set-oriented. You don't work with cursors, okay? So cursors is probably the slowest way to work with linear algorithms. Cursors are slow, but linearly slow. Cross-join is quadratic, for example. This is completely different beast. Linear means you can still improve it with better hardware, right? Anyway, cursors are slow because we don't have positional access. Our Python data frame, we have positional access. Cursor is building positional access on the top of a set. So this row by row, the processing in a data frame would be, let's say, 2 times faster than with cursor. But then data frame with built-in matrix operation will be like 50 times faster, up to 100 times faster. But then set operations in Transact SQL will be another 10 to 100 times faster. You have to think about it. SQL Server is optimized to work with huge data sets for decades. These are data frames, Python, all data science is still working on samples. Statistics is working on samples. They are more focused on having these complex calculations than on performance. That's why we don't have many statistical functions in Transact SQL. But if you work with huge data sets, you should do as much processing in Transact SQL as possible, as long as you don't go to cursors, of course.
I would just add for this approximate functions, the most important reason why, the most important benefit of them is memory usage. So they use log algorithm for memory, and something where you need, I don't know, 150 gigs to get exact number of, approximative distinct count, for instance. For approximate value, you would need just a few megabytes. So compared to this, and you will get acceptable results. So it's not always about the speed, it's more about the memory, but mostly for very large data set, as Dan described, it's both speed and memory. So basically you save resources and you're fine with results. And all my tests shows these results. I never got result which was different than 3% of the especially for large data sets. You can have, more than 10, but for small data set, but you don't care about approximately in that case. Yeah.
Yes. Thank you very much. I didn't know this about memory, but also, I'm usually not so much concerned with memory. As I said, that you work on copy, on separate what I did. And if you do statistics, you are usually more or less alone in the database. But for general optimization, really, really a great tip. Thank you very much.
Yeah.
I will just prepare a small table for just brief introduction of NAS. Let me go to the presentation. So missing values, of course, is can be a big problem. It is not so huge problem anymore because it was in the past, because typically we have a lot of data. And remember, most of the time we are still working with samples. We implement algorithms, create models on samples. What do you do with missing values? If algorithms can handle them, then you don't need to do anything, maybe. What I really like is the second option, filter the rows with missing data. If there is missing data, if in any of the column, you can just filter the row if two prerequisites are met. First is that you don't filter too many rows, which is, as I said, nowadays not a big deal. In the past, we couldn't use this option since data was scarce. It was not, you didn't have billion of rows. If I select 50,000 rows for a sample out of 1 billion, who cares? I mean, if I, the next thing you have to check, is there a pattern? What you do, I typically create a flag in advance, a row has a missing value or not. So simple flag, true, false. And then I analyze other variables. Let's say we have age, we have income. I would analyze these two variables in these two groups. If there is substantial difference, it means that there is a pattern in null, so you cannot simply ignore them. Filter the columns is even worse option. But as I said, most of the time nowadays, filter the rows is very useful. You can replace them with some common values like mean values, even predict new values, but you are losing variability. You can try to build separate models with some columns, with only columns that have no missing values and so on. But this is a lot of work. And as I said, most of the time you can just filter the rows if you deal with huge data sets. You should quickly check if there is any pattern. What about outliers? Well, again, this can be a big problem. Remember this N-scope data set, we got completely wrong picture about correlation between two variables, the fourth pair, because of a single value that was far out of bounds. So first you should check if this is an erroneous value, might be just an error. Again, depends what you are doing, but this is not very frequent. You can even do nothing. Filter the rows with outliers, ignore the column, replace with common middle values, or maybe you can even use discretizing this variable. So let's say income with a very rich person, with Bill Gates, if we would discretize income, let's say in 3 classes, low, moderate, high, this extreme value is then hidden in the last class. Or normalize data values. So it means create with a bijectional function a new set of values in a limited interval. For example, we can use hyperbolic tangent. It can translate values in an interval between -1 + 1, or logistic function translates it into interval between 0 and 1, which could be useful if you don't have negative values. What if you need to create numerics from strings? Well, if we have order, we just use this index order. What if we have nominals? Then we can create what are called dummies in statistical terminology, or dummy variables. These are indicators with values 0 and 1. So you create one dummy variable, so for every distinct state or distinct value of original variable. Let's say color, we have 3 values, green, blue, red, and then we have dummy green, which takes value 1 when the original product is green and 0 when it is blue or red, and so on. And then you can use these variables. But one very important warning here. Remember degrees of freedom. I said they are not really important so much anymore, yet here they are extremely important. Remember that one value is not free, right? So in further analysis, you should use n-1 dummies. Why? Well, otherwise you would get perfect correlation between these variables. Let's say that you would do some regression analysis and these variables would perfectly correlate. If you know blue and red, then you know green color and so on. And you get perfect results which are completely meaningless because this is what you knew in advance. So when you create dummies, make sure that you don't use all of them in further analysis, n-1. One big thing it can be that you still don't have enough variables. This is very much true with Internet of Things, with all kind of devices that are recording something. You usually get time, you get some number, and maybe something else, maybe something like, I don't know, IP address and so on. And it looks like you cannot do much out of them. But if you know what you are working on, you can still do a lot. If you can create derived variables from time, you can create all kind of intervals, you know, like hours, days. Well, time units are always intervals, but then we have also weekdays, and we can say holidays, and we have seasons like spring, summer, and so on. From IP addresses, we can extract geographical features. Then we can also measure difference between two events, so elapsed time between two events. This might be also an interesting variable. What is the elapsed time from previous to the next event? But then, of course, these are variables that are extremely important from a line of business perspective. To find these variables that are important for business area, you have to know very well business area. If you are like independent consultant, like I'm doing these things for many companies, I always insist that I have in a team also a subject matter expert that can tell me what values of variables mean, how things are measured. Look at this first example, very simple. This body mass index or obesity index, height squared divided by weight. I mean, height and weight by themselves don't tell you much about health of person, but this body mass index is extremely important. Let me tell you, this reminds me, we spend a minute on a short, what was this comment is also a bullshit. Let's check the comment. But this is completely different discussion. Yeah, I mean, yes, if you look in the space, the ideal shape is round, so it's wrong, right? We should follow the ideal shape. Anyway, let me tell you this anecdote. So I was riding a bike in some forest road in Slovenia, and I really like to drink schnapps. And I was riding in an area where they have a real speciality, schnapps made of white cherries. This is speciality of some small area in Slovenia. And suddenly in the middle of nowhere, there was a booth with two girls. And what did I think? Of course, in my mind was they are selling schnapps here. So I pressed the brakes so hard that the next person hit me in the back. Was not, you know, not too happy. I immediately started to ask these two girls, so what kind of schnapps do you have? Do you have the white cherry one? And one girl said, but mister, we are measuring body mass index if you wish. Okay, sorry. I'll pass. They're measuring body mass index in the middle of nowhere. Why? So yes, especially geographical data. Now, let me tell you one pretty bold proposition. The more fancy the graph is, the less information it shows. This is with these maps. You know, nowadays we have this very frequent presentation on maps in Power BI and everywhere. It's very popular, but typically people have no idea what they are showing. They are showing data that cannot be compared at all. So, okay, area population density is better than just population in the area, but even this one is typically doesn't tell you enough. Let me give you again a concrete example so you will understand what I'm talking about. You know that let's say in every country people complain about roads. We put so much money there and we don't have good roads and they are always being repaired. So I managed to read last year, I think, in some magazine in Slovenia, explaining how roads are much better in Belgium than in Slovenia. And this is geographical comparison. So I was starting immediately to think about it. That doesn't sound well to me. So let's check some facts. So Belgium has 10 million population, approximately on 40,000 square kilometers. Slovenia, 2 million on 20,000. So population density in Belgium is 2.5 times more dense than in Slovenia, bigger than in Slovenia. Then let's say income is approximately twice higher per capita. So let's multiply 2.5 by 2. So we have 5. Then the configuration of terrain is completely different. I mean, the highest peak in Belgium is like in Ardennes, 340 meters, something like this. I am now in Ljubljana and on 300 meters already, and I'm below the hill, and, which is 1,000 meters and so on. So Slovenia is only about mountains. There is practically no flat land, very scarce flat land. So like building roads here is at least twice more expensive, many more tunnels, many more viaducts, and so on. So let's add factor 2. So we are already at factor 10. But then also, you know, in Belgium, there is no winter. Winter makes a lot of damage on the road. So you have to spend much more money on maintaining them. Let's add another, let's say factor 10, factor 2. We are already on factor 20. We can continue. The more money you have, the less percentage you spend on essential things like food, electricity. So the more is left over for roads and so on. So what are we comparing here? So you see, the comparison was completely stupid. The better comparison would be with countries with approximately similar income, population density, terrain. So let's say in European Union, the comparison of Slovenia would be maybe good with Greece, Portugal, Spain, Czech Republic, and that's more or less it. You know, everything else is simply bullshit. And I see we have a lot of the discussion already in chat about bullshit with body mass index. Yes, I agree, it's bullshit. No, definitely, you know, I see mentioned this like Schwarzenegger would fail the body mass index check. Yes, actually, I fully agree. Now I'm not Schwarzenegger, but I do train swimming for all of my life. And I do also a lot of cycling and some fitness. And yes, for 60 and more years, I have a lot of muscles and my body mass index is high. And I always remember this when I go to doctors. You should, you know, lose some weight. Oh, come on, you know. Did you check that my body is not the same as of the next person there, which really resembles on a barrel of beer. So it's different. I fully agree. I really get angry when they start talking about this. You know. Anyway, as I said, derived variables, extracting fixtures. This is very important that you know the subject area. You know, things like, I don't know, registration plates could be useful for some information, but you must really know how they are created. So in many countries, first two letters are designing the city, but the city where you are living or the city where you took registration plates. In Slovenia, you can take registration plates anywhere. So I live in Ljubljana, but I can take registration plates at any office and I can have different. Okay, let's say 90% you can trust the city. But like in Holland, as far as I know, they are random. Also in Bosnia, registration plates are random, which is another nice story why they are random in Bosnia. You know that they had civil war and that they now split in Serbian, Bosnian, Croatian part, right? Banja Luka like is capital of Serbian part, Sarajevo, Bosnian. So if you came with the car with Sarajevo registration plates in Banja Luka, car was immediately scratched, and the opposite. Now when registration plates are random, people don't have reasons to make damage on cars from different cities anymore. So very small trick that helped a lot. Anyway,
yeah, it's a great thing. They choose the letter which are common in Cyrillic and Latinic, and then you cannot have any idea whether is this car coming from, you know, Bosnian part or Sarajevo or Banja Luka. It was a great. I mean, somebody got some prize for that, you know, for
yes,
inventing this solution.
Yeah.
It's a great
And
thing.
I see. I knew the voice. It's my great friend Milos Radivojevic is with us. Thank you for joining us. If you have questions about optimization, Milos is the man. Milos is the man. So great. Thank you. Yes. But the main point is that you have to know what you are doing. You have to know. It's not enough just to know the technology, just to know the programming language. Now, let me briefly show how we work with nulls. You see, I have a very simple table, 3 columns. Some of them are nulls. Of course, you know is null, coalesced function in T-SQL, and you know that aggregate functions are simply skipping nulls. So if we have average and sum, average is something different than sum divided by count star, because we have nulls. Nulls are simply skipped. Anyway, this depends on language. So let me go to R and let me read this table I just created, right? Let's calculate mean for column 2. And you see, because we have nulls, which means not applicable here in R, the mean is also not applicable. If I want to get the same behavior as in T-SQL, I have to use parameter NA RM equals true. Now we have omit function, which is simply doing omitting all rows where there is any single null in any of the column. Is NA is the test. You see, this is what I like to use, NA omit with large data sets. It's not a problem. Now, of course, let me jump to Python. Read the same data in Python, right? We have isNull test. We have drop NA method in data frame, pandas data frame, and we get the same thing as omit axis column. I have every single column with null, so I simply state without any data, so columns are typically not so useful. Let's calculate aggregates. And we see that default in Python is the same as in Transact SQL, different than in R. With parameters keep and A equal false, then we get similar behavior like in R. Now, let's do some recording. So we have commute distance. I will just use index, right? And then I have possibility to create commute distance integer, but I must know proper order. And then I get ordinal variables. What about dummies? Let's take marital status, single merit. I will use IIF function to create two dummy variables. Let me create a small example of derived variable. So we have base variables, marital status, number of children at home, and I will have number of people in the household. I will say 1, which is person, her or himself. And if marital status is, let's say, married, or I will suppose that I can add 1 person and number of children at home, and I get an example of derived variable. Again, you have to know your data. You know that in many countries it is completely legal to have more than 1 wife. So maybe if marital status is married, it's not so simple just to add 1, right? Of course, it is also possible that you are married, but you live separately and so on. All of these possibilities. Again, you should be very careful. But worth mentioning, we are never searching for completely exact numbers. We are working with probability. So many times you can tolerate some errors with enough data. If you have some idea, let's say how many people that are married live separately. This is, let's say, 0.01%. Who cares? You know, who cares? We can simply add 1 and tolerate this error. Now let me jump to Python. Again, we read smaller data set, define categories, right? We already know that we should define it as ordinal, and then we can simply use category codes, right, to get the actual data. Oh, we have a long, yes, again, we are still with registration plates. Sweden also, UK includes year and registered region. Okay, wow. Sweden also random, except some blocked 3 letters combinations. Wow. Yeah, it can become very, 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 very complex. Also, like, I don't know how zip codes, like in Slovenia, zip codes mean geographical, gives you geographical location. But let's say in Canada, I know they are completely random, don't tell you anything, and so on. So yes, you must really know your data. Now in pandas, we have pandas data frame is very powerful. We have get dummies method, so we can very quickly get dummies of marital status, married, single, also here. And again, let's add derived variable, number of people in the household. So also in R, we have many pre-prepared functions. Of course, you can see from the code that R and Python are more suitable for this kind of things because they have many, many pre-prepared functions, right? But remember that if you are working with really huge data sets, Transact SQL might be the best. With R, we have education properly ordered, defined as factor. We can just use a function as integer and get this education ordered with now with numerical values. The last variable with numerical values. Dummies, we have package dummies, and we will just use function dummy to get also marital status dummies. We have many ways how to create derived variables. I will not go into details. There are really many ways. In basic R, we have within function, but then we have diverse set of packages which are extremely useful for this, but I will not go into details. I will just create this derived variables step by step. So marital status integer, and then also number of people in the household, also in R. So many ways. Now, the last thing I want to mention in this really short introduction to this data overview and manipulation is discretization. Now here I will also introduce entropy. Remember, one reason for discretization could be that we can get rid of outliers. The other reason is, let's say you want to use algorithms like Bayesian inference, so you want to have a couple of discrete values, or you can want to represent graphically data with bar charts. You don't want to have too many continuous variables there. Now, basic discretization methods are equal width. So you have classes with equal width. Equal height means you have classes with equal number of cases in them, and custom. These are very basic. Discretization can go really in depth with more advanced methods. But out of these three, which one should you start with, and which one is good for what? Basically, if you know the area you are analyzing, you start with custom discretization. Why? Because you know something more than you can do with pure algorithms. Think about these examples, age and income. Now, let's look at general data. 1 year difference is a big has big impact and is a big number when you are, let's say, 16 or 17, right? But it's really not important if you are 66 or 67. So what you do when you discretize age, you might want to create narrower classes for younger people and wider for older. Also for income, like, I don't know, 100 euros is a big difference if your income is 800 or 900 euros, but not really important if you have 100,000 or 100,100. Yes, thank you for being here. Enjoy the rest of the day and the weekend. Now, equal width discretization is preserving the distribution. With enough classes, with simple bar charts, you can still see the original shape. What is equal height? What is this one good for? I will start from another side here. Now, let's go back to SQL Server and optimization and indices. Whenever there is any talk about optimization and indices, people start talking about these statistics, okay? So statistics is actually not statistics. It's a very bad example, right? A very bad name, because statistics is very broad term. It's just distribution of keys, and it has equal height distribution. This is what you are told on every presentation, during every presentation about indices and how how to optimize, how this is important. Yet people fail to tell you, why do we have equal height? Why not equal width? There is actually mathematics behind, and I will explain this mathematics. Before that, let me tell you another anecdote. When you are so old as me, then this number of anecdotes becomes quite big. So, I told you, I'm actually, I do applied mathematics. I'm a statistician. I'm one of these few weirdos that actually like statistics. So once I had opportunity, again in Belgium, that I was actually having a presentation about statistics, mathematics. But I'm more known on presenting about SQL Server, right? So in the description, I wrote that please understand this is not about SQL Server, it's mathematics. It has nothing to do with that SQL Server small piece, right? I started presentation with, please understand, this is about mathematics. It has nothing to do with SQL Server, with statistics on indices, okay? It's first minute of presentation. We have couple of presentations in parallel tracks. Please, if you missed the classroom, please leave and go to another presentation. After the conference, I got these evaluations. Two of them were the lowest possible, only once, and common. This was not about SQL Server statistics. Yes, okay, thank you. I don't know how to tell this differently. I tried to explain that I'm not talking about SQL Server statistics, but okay. Why did people stay till the end? I don't know. Okay, what was the point? But still, they just didn't read, didn't listen. Now, what is equal height about? Well, now we are coming to entropy. This comes from another branch of mathematics, information theory. Entropy is measuring the amount of information inside a variable. Now with discretization, we are losing information. And with equal height discretization, the loss of entropy is the smallest. Now let me show you the calculation. This is the formula. You see, it is based on probabilities. So we have probability of each state multiplied by logarithm of this probability. We still use logarithm base 2, although we could use logarithm any base, but Cheryl, which introduced in late 40s the information theory, used logarithm base 2, so it's still here. The point here is that if we have a single state with probability 1, right, then this is simply 0. We have Milos complaining that this is not about sequence or statistics. Thank you, Milos. Thank you. Yes, again, we are here. So now entropy, Sharon already defined that information is the same thing as surprise. This is simply logical definition. If you are not surprised, you didn't learn anything new, right? There is a horse on the 3rd floor. Yes, I know. Who cares, right? And what is the horse doing there? You see the difference in the reaction, right? So now let's go to our products. The question is, why 200 buckets? This is because of space limitation. The more precise statistics you would need more buckets, and then it would be also more expensive to collect it. So this is kind of arbitrary compromise. But why is it equal height? It's because of this entropy. So let's say also information theory, yes, entropy doesn't work well on the continuous variables, but still, okay. So you see, let's say that I have blue and red products in a basket. So I will blindly take out a product. I know the distribution, and I will bet on the color. If I have 90% of blue products, I will bet on blue, and I will get surprised in 10% of cases. If I have 50-50 distribution, no matter on which color I bet, let's say on blue, I will be surprised in 50% of cases. If I have, like, say, 30% blue and 70 red, I will bet on red, and I will be surprised in 30% of cases only. So you see, the maximal possible surprise is when I have 50-50. Now let's add third state, green products. Now maximal possible surprise is 1/3, 1/3, 1/3. I can still bet on a single color, so I would be surprised in 2/3 of cases. with 4 distinct values in 3 quarters. So maximal entropy raises with a number of distinct cases. So when you do binning, you are losing some entropy, but if you do equal height binning, the loss is minimal. And what is good thing also is we are working with probabilities only, so we can easily compare, in an easy way compare relative entropy compared to maximal possible entropy between continuous and discrete variables, also strings, any variable can be used. So let's do this. And let me start again with SQL Server. Okay, binning, okay, is like this is basic data by age. Equal with binning is not simple in SQL Server. You have to calculate the interval and then do the binning, right? I just ordered by new ID to get only top few rows. So I see I have different bins. Equal height is extremely simple with the entire function. And we can see that we get equal height. Okay, first classes get these additional cases. Custom binning, again, with case expression. This probably can be the best one when you know what you are analyzing, when you know more than SQL Server are on Python. And we have custom binning. So maximal entropy for different number of states, like this calculation is very simple. So for 2 states, it's just logarithm of 2. For 3, it's just logarithm of 3. This is just simple mathematics with logarithms. So these are maximal possible entropies for 2 distinct states, 3, 4, 5, and so on. Oh, we still have some interesting advices. Fastest way to get a discrete approximation for a single column, just grab the statistics. Yes, of course, very, very good method. Now let me go to R. We have cut function that can do automatically equal with binning, which is in this example of H, you see very inappropriate. Last bin has only 33 cases. Now equal height binning, interestingly, there is no function in core R. I have here explanation. I will share this code. I will send it to Magnus, or you will tell me where to share. Or I can even share it here later in this chat. But this is step by step how I created function equal height binning, right? That will do the same thing as n-tile in Transact SQL. And let's check also in Python. So we have equal with binning, we have cut method. We have qcut method that is actually doing the kind of equal height binning, not completely the same, because let's say one value is always in a single bin. So 31 is in the first bin. They are opened on the left side. With R and SQL, 31 was partially in the second, partially in the third bin, right? So it's not completely equal height, slightly different. Custom binning, we just fit cut function with limits for custom bin. And let's plot it. And this is custom binning of H, custom binning of H. So I have my arbitrary defined classes. So you see the last class is from 54 to the highest value, and we get a better distribution. And let's go to R. I will use RevoScale R library for a moment. So this is H in equal heights bin histogram. Yes, expected. Let's do with cut function custom binning. Again, similar like in Python, expected. Now, let's use also desk tools, which we already know. Number of cars owned we have histogram, but we can also calculate mean, standard deviation, and coefficient of variability, which is 0.75 in this example here at the bottom, right? Now, let's calculate this for bike buyer. We can create histogram, calculate coefficient of variation, which is bigger. But what about marital status? Well, marital status is a string, MS. So we can only show histogram and counts. We cannot calculate means, but we can calculate entropy. So I will use from desk tools function entropy and calculate absolute entropy of number of cars owned. I will store these frequencies in an object. And then I will calculate maximal possible entropy for 5 states and relative entropy. And let's do this for all 3 variables. And now I can compare relative entropy. And we can see number of cars owned has lower relative entropy than marital status, which has lower than bike buyer. And you see now I could finally compare variability, or even better, entropy of variables that are both strings and numbers. And I guess, okay, lunch break is probably already over. So